program translation. This is all about how we take a computer program and turn it in from text-based format that we humans write and turn that into a format that the CPU can run in binary code. And there are different types of translator, and we're going to go through all of them. So at the moment, we're just going to have a look at just a general overview, and then we're going to go and look specifically at the assembler and how that works. But before we do that, we want to consider just computer languages. So we're going to start off with the idea that, as it says here, all computer programs are just a list of instructions that the computer works through in some kind of sequence, and the sequence is controlled by the code statements, and we write them in a specific language, and each language has got its own syntax rules, and I'm sure you're super familiar with this. And some languages are very, very specific. The example I've given here is Fortran. Fortran is a portmanteau of formula translation and is designed for scientific programming. So, for example, a lot of the apps that the Met Office are using in their climate change modelling and their weather forecasts are written in Fortran. And then you've got Java, which was specifically designed originally. Well, JavaScript is probably a better example. JavaScript is a language that is specifically designed to make web pages interactive, but it can be used for other stuff. And then you get general purpose languages like, as it says, the two examples I've given there, Visual Basic, C++, we put Python in that category, put C# in that category as well. So these are multi-paradigm languages. So you could use that. You can use them as if they're procedural. You can use them as if they are object-oriented. You can write event-driven programs. You can write batch programs. We can write all sorts of different stuff with those kind of languages. So the very first computer language we need to think about is machine code. And of course, machine code is the code that is in binary format, all ones and zeros. And it's the language the processor runs. And you can usually take one step back from the binary and program in hexadecimal if you want to, and that makes life a little bit easier because you get more variety in the codes, but it is still, nevertheless, it's all numbers, and it's quite difficult if you're not really familiar with that environment to work with this. Now you can, one example where you will see hexadecimal is in some higher level languages. It is possible to embed machine code components into your programs if you want to particularly optimize part of the code, and in that situation you'd probably code them in hexadecimal. Now, the other kind of thing we need to consider with machine code is when you write a program, we don't need to translate it because obviously it's the code the CPU runs, so it can just pick it up and run it. But writing it's super slow. And because it's so far detached from our kind of normal human experience, it can be very, very difficult to spot errors in your code, and it can be that causes loads of errors, which makes it quite difficult to produce. But one of the other key problems with machine code is that it is CPU specific. So if you have targeted your code for a particular type of CPU, you're not going to be able to port it anywhere else. It's going to need completely rewriting, and that's rather tedious. So to make life a little bit easier, the next step up that we move up to, and if you like, it's like a second generation language, is assembly. So back in the late 50s, early 60s, when Grace Hopper and people were working away on their machines, they would have primarily coded in machine code and then later assembly language code. And then eventually Grace Hopper created the world's first compiler, which could take text-based code and turn it into machine code to create an executable program. That's quite a major achievement, one on which you could say the whole of the tech industry is based. But in assembly language code, we use mnemonics, and again, you've seen this before when we spoke about assembly language programming. So mnemonic is simply a text representation of a machine code command, and they tend to be some of them can be fairly obvious, as the two we've got there, add and subtract, but some of them can be very cryptic, like BRZJNE, ADC, and so on. They're not necessarily, it's not necessarily obvious what they do, but when you kind of know vaguely what CPUs can do, it's kind of usually fairly clear. So This overcomes difficulty of coding everything in ones and zeros, makes life a little bit easier, and that means it's quicker for us to write our programs, and we're going to make fewer errors. Still got complete control of the CPU, and we've still got this one-to-one relationship. We write one instruction, the CPU carries out one operation. So we've got complete control of the machine, full access to every feature of the CPU, which you don't necessarily have in high-level languages. But the problem now is we need to take this text that we're going to write and we've got to turn it into the binary format the CPU can run. And to do that, we need a translator called an assembler, which is what we're going to look at in the next presentation. So in assembly, easier to code, easier to remember mnemonics, don't have to keep looking them up, complete control of your CPU, but CPU specific still, and the code can be quite difficult to get your head around if you're not used to that kind of environment. And assembly programs tend to be very, very long, and part of the reason for that is because of this one-to-one relationship between the instructions that you write and the machine code commands that have to be carried out. So if you want to do something simple like a fairly simple loop, say, I don't know, that runs through an array and totals a load of values up, then that's actually going to require quite a lot of assembly code to do that, whereas in you could probably do that in 2 or 3 lines in a high-level language. But then we get to the high-level languages, and these are languages that are used to generate the bulk of or account for most computer programs that are being written. And in a high-level language, you're going to write in some form of language that is a lot closer to English than assembly code. And the statements, as it says here, are completely context-free, so there is only one interpretation for each statement that you make. But the idea here is that commonly used operations like repeating things in the form of iterative loops, making decisions in the form of selection statements like if statements and switch statements, case statements, those kind of things are included in these high-level languages, and we can use those. And lots of kind of commonly used constructs have been turned together into high-level code structures. Now, the thing about these is high-level codes are much easier to read, so we can code a lot faster, we can make fewer errors. They are designed, but one line of code that we write may generate many, many lines of machine code, and that means that we haven't now got total control of our CPUs. There is the code that we write will, if it can be turned into machine code, it will always work. It's just a question of how efficiently it works, and it may be possible to produce a better, faster, smaller program using machine code if you know how to do that. But the problem we've got now is, again, we've got to turn this code into machine code, and that is a lot more complex than the previous example where we were looking at the assembler. We're going to have to either compile it or interpret it, and we'll look at how those work in the future. But we talk about these as high-level languages because we are now several layers detached from the control of the CPU. And as I said earlier on, in a high-level language, you don't necessarily get direct access to the hardware. We don't get direct access to all features of the hardware, and therefore there are certain jobs you might want to do that you can't do, such as, for example, control a washing machine, if that's what you're after doing. First and second generation languages we normally talk about as low level because you are directly controlling the CPU. Everything else is high level. Now you will see quite a few articles on the World Wide Web where they'll talk about the C programming language, and they'll tell you that the C is a low level language. I would heartily disagree with that, and the reason is because if I can get a pen up on the screen here, which I can't seem to do. The reason I would disagree with that is because of this thing here, which is the one-to-many relationship. If you write a C program, it does still need to be turned into machine code, and therefore you don't have complete control over the code. And there may be operations that you wish to perform that you can't do in C, which you can do in machine code. But the reason a lot of people will tell you it's a low-level language is because the Unix operating system was originally written in C, and therefore you can do a lot more with the C language on a Unix box than you would be able to do, say, in writing a program in something like C# on a Windows machine. And it's simply because you won't necessarily be able to make direct operating system calls on your Windows machine, but you will on your Unix machine. Anyway, let's move on. A lot easier to code. Programs can also be portable in the sense that the source code is now portable. We can write source code on one machine, we can compile it up. You might be able to take that source code off that machine, move it onto another machine, compile it up there. And again, C is a language where you can do that. There's a standardized version of C, ANSI standard C. And if you set the right flags on your compiler, you can get it to enforce the use of only ANSI compatible code. And that way you can pick up your C program off machine A, move it onto machine B, recompile it, and it will run without any changes. We've also got lots and lots and lots more programming structures that make life a lot easier. We've got things like arrays, which don't exist in low-level languages. But we do have to translate it, and that can take ages. Just to give you an idea, if you want to compile up the full version of the Linux operating system, and you've got a moderately powerful PC to do that, that machine would probably be busy for a good few hours doing that, because there's a lot of work that needs to be done. We also may find the programs run more slowly, and that's primarily the machine code equivalents, and that's primarily because we are maybe generating inefficient machine code, which a really good programmer could improve on. And we also need to have very skilled programmers who really understand how CPUs work. And quite often, as it says here, programmers will need to know more than one language, because, for example, if you want to if you want to write like a Windows app that talks to a database, you're probably going to have to know both how to write your C# program and also how to write your SQL code, and then you'll have to learn about the kind of mechanisms you're going to use to talk to that database, your kind of middleware, and that means that we have to start getting multi-skilled. So it doesn't kind of completely remove the problem of making systems completely accessible to users. And there's new languages coming along all the time, so it can be quite difficult to keep up to date. And what you'll probably find is that when you learn one language, you'll learn it pretty well, and then you kind of learn another one, and you'll then start making loads of mistakes because you keep on forgetting syntax or getting the syntax wrong, and then you learn a third language and the fourth and a fifth and so on. But in essence, they all conform to fairly standardized methods of working. And once you've learned how to code, for example, procedurally, you can just take that knowledge and transfer it from one language to another. So that's what we talked about. So we covered a little bit about what these translators are, which is basically taking source code and converting that into object code. We've spoken a little bit about how you can take the relationships between assembly and machine code, and we talked a little bit about the use of the assembler. And talking about that, we haven't really addressed this point here, though, the difference between interpretation and compilation yet. And the key difference here is that in some languages, what we're going to do is we're going to translate the code at runtime. So we'll do that statement by statement. That's interpretation. So if you think of like, if you watch, say, the UN proceedings at the UN, you'll have someone speaking, and then lots of the delegates will have their headphones on, and they'll be listening to someone who's simultaneously translating what the speaker's saying. And that, to me, is a kind of an example of the kind of way that an interpreter works. It reads a line of code, turns it into machine code, runs it. Reads a line of code, or I should say a statement of code, turns that into machine code and runs it. Compilers work very differently. What they do is they pick up the program, they attempt to translate it, and if they're successful, they produce a single executable program, and then that program can run, and that program will be saved in machine code format, and we can run that without any further translation. And that's that. Now, when we're going to translate, we need to understand that CPUs can only run machine code. So we need to convert everything not written in machine code into machine code before the CPU can run with it. So we write source code, that's text. We then translate it, and that produces our machine code that the CPU can run. And we've got the assembler, as we said, that turns assembly language code into binary code, and there's a one-to-one relationship between the instructions we write in assembler and what we get in binary code. We have interpreters, as we just said, that they pick up a high-level program language and they then convert them one line at a time. And an example of that would be Python. then with a compiler, we're going to take our high-level code and we're going to convert the whole program in one go into machine code. And then the machine code can run independently of the original program. And the example I'm going to use there is C. Now, be aware that if you read up anything about C# or Visual Basic or Java, you may get, it may sound a little bit confused, and that's because those languages do what you might consider to be a hybrid combination of interpreting and compiling, which we will cover shortly. So interpreters run, as it says here, they go through and they translate your program statement by statement, but because they have to translate every statement as they run, they are slower. And part of the reason for that is because if you're inside a loop, for example, it's going to translate the code inside the loop many, many times as it iterates around the loop. But they are really useful, as it says here, for development, because as soon as they hit an error, they'll stop and they'll point to exactly where the error is. And sometimes you can correct that error and carry on. And the other kind of thing is to actually do the translation itself, you don't need a lot of memory to translate a single code statement. However, you do need the translator installed on the machine. So you need the programming environment installed on the computer so you can run it. And that programming environment itself may be quite big. So although the program itself that or the statement you're translating doesn't need a lot of memory, if the translator does, you're going to need a fairly powerful computer to run it. And you will need to install the interpreter to run the program. And if you haven't got the interpreter, you can't run that program. And as well as that, you also need the source code. But we don't find out about errors until we run the program, which may be a problem. Now with compilers, we compile it once and then that's it. We can forget about translating it again. Never needs to happen. But compilers will give you all your errors in one go, and that means you can have one error at the start of the program that causes lots of carry forward errors, and you then may end up with causing, say, one or two errors in your source code, and then you get an output that says you've got 1,000 errors in your code. So you get these spurious errors reported, like, for example, if you start a comment but you don't finish it, that can have very interesting consequences. So you do need to watch out for that. Something else is that when you have compiled your program, you can just give your program to someone else and they can run it. They don't need the translator, so they don't need the programming environment installed. The code will always run very fast because it doesn't do it's not translating at runtime, unlike an interpreter. And but the problem is that when you make a change to your program, it completely invalidates all the source code, or sorry, all the executable machine code. So you're going to need to completely recompile it. And that, as we said that compilation can take a lot of time. The kind of stuff that I used to work on, typically if you wanted to compile a program, it'd take about 10 minutes to compile. So you could like change one line of code, press compile, and have to wait 10 minutes to get a result. And at that point, it then tells you've missed out a semicolon or you've got an extra bracket in place. So it can be quite a time-consuming process. So you don't want to use the compiler as a kind of debugging tool. You want to use your own knowledge to do that. So this is an example of a piece of assembly language code. I actually stole this from a Hello World program. So the idea is in this program, MSG would be a memory location in RAM that holds the message Hello World. DX is the a kind of register, and then in this case we are taking a 9 and we're moving that into AH. So this statement here, for example, mov AH9 is equivalent to a high-level instruction that said AH equals 9. Incredible, isn't it? And then this is actually causing saying I want you to raise an interrupt, and it's this interrupt number here. So that will actually cause the operating system to do something, which in this case I believe is the print instruction. That would just tell it to take what's in register AH and dump it out to the screen. And then in this case, we're going to take this instruction and move it into AH, and then when we call this interrupt saying call the operating system, it'll actually terminate the program. So that's like saying end, those two lines there. Anyway, there's our machine code program, and what we've got to do is we've got to turn this into binary code that this CPU can run. And there's quite a lot of things are going to have to go on here. Now I'm just going to kind of add a couple of extra things here. I'm going to have a label, and I'm going to call this start here. And then down in this section, I'm going to have a label called end. Okay, and they're just purely for my convenience to help me understand what the code is doing. I might, if you recall from last year, one of the things we can use in machine code is there are often commands which are either called branch or jump commands. So I'm going to use JNE, and if I say JNE start, what will happen is my code will what will happen is when we go to this line of code here, it's going to examine the accumulator, and if it's not equal, in fact, I'm going to change that to J and Z because it's a bit easier to understand. If this is saying jump if not 0, so it's going to look at the accumulator. If we've got non-zero value, it's going to jump back to start. So this would actually cause it to go back to the start. And if we've got some operation in here, say where we are doing something that's going to change the accumulator value, like for example, decrementing a loop counter, you can use this kind of construct to implement a loop. Something else you also often use jump operations for is you might have a label. So you might have a line of code here. I'm just going to kind of say move dx r0. We'll have a label called first, and then in here I've got an extra e on the move. My apologies. Otherwise we'll have dx. We'll move r1 into dx. Messing this up, sorry. That's going to be called first. This one's going to be called second. And I'm going to say JIP, jump if positive, second. And what will happen here is we'll look at the accumulator. If the accumulator contains a positive value, negative and positive value, we're going to move execution forward to this line of code here. So we're going to bypass this one. If the accumulator contains a value that's either 0 or negative, we're going to run this line of code here. So the idea is this is effectively implementing an if statement, an if then else statement. But anyway, there's a few things there. So we've got in assembly language code, we have labels. We have comments like this one here. We have this is a statement. This is the actual code statement here. And the code statement consists of two parts, if you remember from last year. Operator, and this is telling the machine what to do. And then we've got the operand over here, which is telling these are parameters for the operator to operate on. So this is the data we're working with. Most instructions will have either two operands like this, operator operands. We've got two operands for this statement here. This operator here, int, has one operand. But what's going to happen is when we assemble, the first thing we'll do is we will take, we'll go and obviously allocate memory and disk and so on as we need to. The first thing we're going to do is we're going to strip out all of the white space in our program. So we'll just get rid of all of the code state, all of the variables. We'll also get rid of the white space because the machine isn't interested in that at all. And so we've just basically cleaned up the source code. So all we're left with is executable statements the program has written. I'll get rid of that line at the top there as well. So remove white space and comments. Next up is we are going to go through this here, and we will replace all of the operators with their equivalent binary codes. Now, just to save a wee bit of time, I'm just going to make this nice and simple. So in my case, my mov command is going to be 8 ones. It wouldn't be, but it's going to be in my case 2, 3, 4, 5, 6, 7, 8. So every time we see the operator mov, we will put this in here, like so. And then int is going to be 1, 0, 1, 0, 1, 0, 1, 0. So again, we're going to do that there, and we're going to do that there, like so. And then JIP, that can be 1, 1, 1, 1, 1, 2, 3, 4. So now we, you notice all the operators have gone. And these are standardized codes that we use for all sorts of, you know, it's just a straightforward lookup table. What's going to happen now is we've seen the number 9 here. So in 9 in binary, I believe, is 1, 2, 3, 4, like that. And now we're left with a few values that we can't really do anything with because these are all user-defined items. So we're going to generate a thing called a symbol table. And in the symbol table, we want the symbol, and we're going to give it a thing called a token, which is a binary code. So these are program specific. What the assembler will do is it will start reading through the program, and it's going to look at, it's going to see we've got a label here. So I'm going to give that label, I'll give that the value of, that is a just a line of code here. So in my table, I've kind of said, okay, I've added to my symbol table the value. We've got start, and I've given this token here. Next up, we see this this value here, dx. So that's a variable, and I'm going to again give that an address, give that a number. Whoops. And we can now put this here, where the dx is right there. And you'll notice that we've used dx elsewhere in the program. So I'm going to take that value and I'm going to put it in here and here as well, and so on. So what's going to happen is we're then going to replace this MSG. We're going to replace the AH. We're going to replace these hex codes, and so on. And we're going to replace all of these with and my apologies, I'm being rather dim here, aren't I? That would obviously not have a 2 there, that would have a 1, 0. This being binary and so on. So we're going to replace all these, and the other thing I haven't alluded to is this comma here. We would replace that with the standard code number, which will come out of the straightforward lookup. So we've gradually gone through here and we've replaced all of this code with binary codes. And I'm just going to put in some arbitrary numbers here that really mean nothing. But the kind of point I'm trying to make is that what we're doing is we are systematically turning everything into binary. Once we've done this, what will then happen is we'll do some rudimentary error checking. So the assembler knows, for example, that this command here, which was the mov, this should have 2 items. This one here, we'll call this one A and we'll call this one B. And there's a comma in the middle. So it will simply say, does this statement conform to that syntax rule, yes or no? And if it's got an incorrect number of operators, you'll get an error message. If it has got, if the comma's missing, you'll get an error message, and so on. So basically, is the statement formed properly? And if it is, it's okay. It passes the syntax check. And if it isn't, for example, if we missed out the comma there, we would fail the syntax check, and that would actually cause an error message to be written out. Now, assuming we get no errors though, what will then happen is we have a program that is almost perfectly written into it's ready to be written into executable format.